Hello.
Hello, Mr. Eric, Mr. Ryan, right?
Yeah.
Okay, so binary search tree. Let's say we have two binary search tree, yeah? 10, 9, 11, and then 7, 5, 8. Okay, and then we have another here, 4, 6. Right? Okay, let me put another one. Is this a binary search tree?
No.
Why is that?
Because
Why is that?
16 is not smaller than 7.
Well done, that's a good spot. Okay. On the left tree, the nodes have to be strictly smaller than the parents. The yeah. So on the left side, put in other words, on the left side, the nodes has to be.
Can this note be the same as that?
Well done, that's another question. No, because there's no duplicate. Yeah, there's no duplicate. All the nodes needs to be unique. Right? If it's a duplicate, it's not strictly. So what we say in the binary search tree is the nodes have to be strictly. What's strictly smaller? Right?
Means
And then there will, on the right hand side will be strictly bigger. Okay, so that's good. So if we want to perform what kind of tree traverser gives this sorted list? I mean, if it's what order, then it will be in order. What order would be left? Anybody?
in order.
In order, in order. So what in order? In order is what? We visit the left tree, and then we visit the current node, and then we visit the right tree, right? Why is it called in order? Because the node we are visiting is in the middle. Let's call it in order, right? Yeah? So the left bit and the right bit are recursion. We can do this recursively, yeah? So we recursively visit the left tree, and then we visit the node, and then we visit the right tree, yeah? So this will be easy, yeah? How do you implement the in order? Define in order, easy, and then root and run, yeah? So if it's not empty, we just return. We just return empty list. Otherwise, we return in order root left plus root value plus in order root right. Right? Yeah, this is very trivial. Right? Come on, Ryan, Eric. Yeah.
Trivia.
What's trivial? Yeah, it's
It
not.
means ugly.
It's not difficult, right? It's not
It
difficult.
means
Okay?
it's another word for ugly.
Okay, yeah. Okay, so we probably talk about this. This is recursion, yeah? Recursion. We call it in order twice. To visit the left tree and to visit the right tree, okay?
Yes, thank
To visit the left tree and the right tree. But we can do this iteratively, yeah? Iteratively, okay? Okay, so we can do this iteratively as well. Huh? So we can do this iteratively. The thing is that we keep visiting the left tree because that's the smallest. That gives us smallest. And then we push it into a stack. We push this left in a stack. And then we travel. Every time we take one out, and then we visit the right tree, right? Because the right. Look, 7, we push this in a stack, yeah? So 7, 5, 4. Right? And then we take the 4 out. This is 4. Yeah, take the 4 out. And then it doesn't have the right. Okay, then we take the 5 out. Take the 5 out. Yeah? And then we go to the right. 6. Right? And then we take it 7 out. And we go to the right. Which is 8. Right? Yeah? Define in order. Let's do there. Okay, so I write a recursion here, just to do the comparison with the root. That will be very easy. Yeah? If not root, let me write it again. Yeah? Not root. If it's empty, we return empty list.
Yeah, whatever.
And then return in order. In order what?
Whatever.
In order what? Plus.
In order plus
What?
root dot value.
Plus in order. So what should I put here? I wrote this 5 minutes ago on here.
Right, left,
Here is what?
left.
Yeah, root on left, yeah? And then what's here?
Right.
Root on right, yeah? These two are recursion, yeah? Doing this recursion. Yeah, recursion. Okay, and then this is the iterative answer, empty one, yeah? So while we have a stack, empty, while root or stack. Now we want to go to the left as much as we can. While root stack dot append root dot stack dot append root, and then root equals root dot left. Right? And then we take one out. Root equals stack dot pop, the last one, and then answer dot append root dot value. Okay. And then root equals root dot right. Okay. This is its iterative, and return answer. The time complexity both are the same, but practically speaking, the iterative one is faster, right? Because it doesn't have this calling stack overhead, right? This one recursion. Recursion can be sometimes very costly. Yeah. Okay, so let's coming back to today's question. So we have two binary search tree. Let's just put another easy one. So if we want to return all the elements from both binary search tree, but in order. So what do we have? Look, this binary search tree, 0, 1, 2. This binary search tree, 3, 4, 5.
0, 1, 2, 3, 4, 5.
Exactly. Easy. So how do we do this? Any idea? Come on. This is
in order, left and right, and then merge them.
And then how to merge it? Well done. Wow, that's excellent. Yeah. So this is
That's what I'm smart, obviously.
so basically this question we have talked about separate, two steps separate before, right? So first step is in order. We all that's very obvious. We know that, right? And once we got this in order, we have these two sorted this, right? And the next step is to merge them, right? Yeah. So if we don't use this, if this is a two arbitrary binary tree, not a binary search tree, then the only way we can do it is to traverse both trees, and then we just merge them and then sort it. We need to sort it afterwards, right? If they're not in order, so we can do any arbitrary tree traversal, depth search, pre-order, in order, post order, or all the level by level order, right? The level by level breadth search order. And then we got a two list which is not sorted, and then we can merge them. And then we will do sorting. So what's the time complexity if we want to do the sorting?
O and log n.
Where the O and log n. So for example, the first binary tree, if it's n nodes, and the second one is m nodes, if we will use the naive one, if we are not making use of the fact that they are both the binary search tree, and we can do this in order thing to make it a sorted list. If we are just doing this, brute force, just randomly, just do some random traversal to make sure all the nodes are visited, and then we combine two nodes, and then we just can do this sorting. So the time complexity will be O n plus m. That's the total number of nodes, and log n plus m. Yeah. This is the traversal. But the thing is that it's a binary search tree, so we can do this in order, and then we can merge it. Yeah. So okay, we can have these two in order things. So A equals in order root 1, right? And then B equals in order root 2, right? And then we can merge this because A and B, this is already sorted, right? So the time complexity. Okay, let me write this merge first. Okay, so this one is easy. I'm going to erase this bit, and this is for the iterative in order thing which we're going to use later. Okay, so let's say A equals in order root 1, the first tree. Yeah, B equals in order root 2. Okay, and then we have a length LA LB equals length A, length B, and then we have this answer equal empty list, and then I equals J equals 0. How do we merge two sorted lists? Any idea? If they are two sorted, like 0, 1.
You see which one is bigger.
Yeah, look, 0, 2, 4.
Down, obviously.
Okay, and then 1, 3.
I'm smart.
Yeah, wait on, look, these two sorted lists, yeah? Look.
Yes.
0, 2, 4, 6, 8, and 1, 3, 5, 7, 9. So we have 2 pointers. 0 is smaller than 1. We put a 0. We move the pointer, the first one, to 2. And 1 is smaller than 2. Yeah, and then go this way. That time complexity is O n plus m. Yeah. Look, if there are n nodes in the first tree and n node in the second tree, so time complexity to merge two sorted lists, two trees would be O n plus m. Right? O n plus m. And to the time to travel to do the in order is on for the first tree, om for the first tree, for the second tree. So the time complexity will be on plus m plus m plus m, o2n plus 2o2m, which is on plus m, right? Because we drop the constant when we talk about the time complexity and specific complexity. And then let's go back to this one. I'm going to quickly very merge. Y is I smaller than LA and J smaller than LB. Then we check if AI is smaller or equal than BJ. Then we merge we take the smaller one, answer dot append AI, and then move this pointer I plus equal 1 else. We take the smaller one, take the smaller one for which is BJ, right? In this case, BJ and J plus equal 1. Okay, and when we are outside the while loop, so there might be remaining elements because the length of the two sorted array might not be the same, so we need to append the rest, right? So if I is smaller than LA, then we answer dot extend. We using the extend functions to take whatever is remaining, which is AI to the n. And then the same. If J is smaller than LB, answer dot extend. Extend. What's extend mean in English? BJ to the n.
Longer. Make it longer.
Make it longer. Exactly. Yeah. Okay. So return answer. Okay. Yeah. Look, we have this in order, iterative in order, right? So another way is we can do this iterative in order on both trees in parallel. Okay. This is a little bit advanced topic. It's more complex. Yeah. But it's not easy to think of. But this one, yeah. We have talked about doing in order, recursionally or iterative. And then once we have this in order, we have to sort this, then we can merge it. Yeah, we talked about these two topics before, right? Yeah. So today, nothing new. It's just to combine these two steps. Okay. So now the thing is that look, we have this in order. We can do this iterative in order with two binary search tree in parallel. So how do we do this in parallel? So we can do this st1, yeah. Then we have the st2 equals, okay. And then while root or st1, yeah. Root 1, yeah. There are two trees, yeah. Actually, there are two trees. Root 1, root 2. Root 1 or st1 or root 2 or st2, yeah. And then we do this. We need to copy these two, yeah. YL1, root 1 the left, and then we need to copy these to root 2, okay? There's another one for root 2. Okay? And then now we have to take the smaller one. So how do we take the small one? If not st1 or st1 dot value, if not st1 or st1 dot value, st1 the stack minus 1 stack dot value is smaller than st1, st2 minus 1 dot value. Yeah? Okay? So the thing is that what? If st1, yeah, if st1 is smaller than st2 value, then we take the smaller one, right? If not st2 or st1 and st1 the value is smaller, then we take the st1. We take the node from the first tree, which is the root 1 or st1 dot pop, and then append root 1 dot root. Else we take the root 2. Okay, I'm going to write this here. It's too squishy here. Okay. So we are combining two iterative in order in one single function. So we're checking every time we push the left node to each stack. Yeah, st1, 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 and st2. Okay, st1, yeah, and then we have another one for st2, which is the root 2. And then we need to check if the value in the first stack is for the first tree, is smaller than the second one, we take the node from the first one. Otherwise, we take a node from the second one, right? Do I make myself clear? Okay, so it's too squishy here, but basically that's what it is. So every time you see this, you need to duplicate it for another tree. Yeah, and taking. This is the taking a node from the stack, but we need to check which stack has the smaller node, right? So if the second stack is empty, then we take the first node. Or if the second stack, the node of the if the second stack is empty, if we take the first stack. Or if the second stack is not empty, but the first stack is the value, the top of the stack is smaller than the top of the second stack, then we also take the first stack, the node from the first stack. Otherwise, we take the node from the second stack. So this time complexity is the same, but it's one pass. The advantage of this is one pass. For the previous one, it's two pass. Why we say two pass? Because the Inorder, right? Inorder one pass, right? That's one pass, and then we merge it, second pass. Yeah? This one is one pass. Okay, what have you learned today?
About
What's the problem?
there are two binary trees.
Binary search trees.
Yeah. And then we thought
We want to return all the elements from both trees combined, right? Yeah. So, what's the way? What's the algorithm?
you do in order for both of them and then merge them.
Yeah, and the time complexity will be O n plus n, right? Yeah. And what's the second one? Do you understand this one, or is it too difficult for you? It's fine if it's too difficult because this one is out of scope.
It's medium.
It's medium. Yeah. So we do this one is iterative in order. So we are doing. So basically this one is what we are doing the in order for both trees in parallel. Yeah. But during the in order, we just take whatever is smaller, right? And this one is it's not recursion. It's iterative using the stack, right? Okay, that's it for today. Bye bye.
Bye bye.
Bye bye.